Here we're looking at a problem from the fluids unit. This is fluid dynamics, which means fluids in motion. We are given water moving to the right through this underground pipe segment A, and then it's going to turn upward and exit the pipe into the air through segment B. And things given in the problem, we have the change of height from A to B. We have the density of the fluid. We are given the thickness or cross-sectional area of each pipe segment, that's A and B. And then we are given the speed that the fluid leaves the pipe here at segment B. What we're looking for is the speed at point A when we're underground, and also what is the absolute water pressure in the pipe underground as well at point A. Chose this question from a 2009 AP Physics exam. I thought it was a good question that paired two major fluid dynamic concepts together. That's the continuity equation and Bernoulli's equation. We'll need both of those. Getting started with question A, I am copying here the continuity equation. This is about the conservation of volumetric flow rate, stating that the area of the pipe segment multiplied by the velocity of the fluid through that segment, that is a conserved quantity, and those two things multiplied together should be equal everywhere. Well, we have two pipe segments, A and B. You can see that segment A is a little wider in the picture, B a little narrower. We are given those cross-sectional area values and want to use them. And now we have a place to do that with AA and AB. We are also given the speed at point B. And so I'm going to plug those three things in. And the only thing missing in our line is the speed of the water as it travels through segment A. I'll call that VA. Performing the calculation gets me an answer of 4.1 meters per second. And that will be the answer to question A. Moving on to question B. We are now looking for the absolute water pressure, which is like the total water pressure in the pipe at position A. To get there, I'll first establish some heights. I'll say pipe segment A underground. This will be my reference point or a height of 0, and that would put segment B up here at a height of 0.5 meters. This is Bernoulli's equation. It is basically conservation of energy in fluids. So if you need pressure for a moving fluid question, this is the likely connection. P1 is the pressure we're looking for. That is the pressure in the first segment of our analysis, and that's segment A. And to solve for that, we'll have to analyze this middle term, which is going to be potential energy related or height related, and this third term, which is motion or velocity related. So these three added together at segment A will equal these three added together at segment B. Some of these terms may increase, some may decrease, some may remain the same, but the totality of the three added together are equal, and that's the conservation aspect. Here I'm just making it look more specific to our problem, replacing the 1s and the 2s with A's and B's. This term here, potential energy for the fluid at segment A, I'm going to cross that out as it is equal to 0. We are at a height of 0. So there is no potential energy in terms of vertical position for the fluid at this point. Here I'm copying what's left. Now let's establish our given information. The pressure at position A, again, is what we're looking for. So I'll put a question mark next to this term. The density is 1,000 kilograms per meter cubed. That's for water and was given in the question. The velocity at segment A was what we solved for in the previous question, 4.1 meters per second. For the pressure at position B, I will be using 100,000 pascals. This is a known number for Earth's atmospheric pressure. Observing the fluid leaving segment B, look what's above segment B. There is no fluid above B pushing down on this point. Rather, there is only air above this point, so we say that this pipe segment is open to the atmosphere, and we'll use our atmospheric pressure value. Earth's gravitational field strength, we'll use 10 newtons per kilogram here. The height of position B, again, is 0.5 meters above our reference point. And we were given the velocity of the fluid in segment B as 8.2 meters per second. So reading across this long line, the only variable I do not have information for is the pressure at position A. Performing the calculation gives me this answer of 130,000 pascals. So in future problems that relate to moving fluids, when you see pipes changing their thickness, we want to think about the continuity equation so we can get the cross-sectional area or thickness involved. When we see pipes changing height, that's usually a giveaway for Bernoulli's equation, so we can get those height variables involved.
If you found this video helpful, then I have other resources that you may be interested in as well. For more information, check out my website, shoot me an email, or follow me on X and Facebook. All of the links can be found in the video description.